I didn't produce this first picture, but as an interesting picture bottom right, which is British Columbia and Washington State in the US. And I don't know if you've been following the news, but they've been having an enormous heat wave recently, temperatures getting up to 50 degrees centigrade. And whilst we often associate climate change with storms and stuff like that, heat waves are actually far, far more dangerous in terms of their impact on human life. So it's really interesting to put this up, and it's very relevant to me because I'm actually half Canadian. Most of my family live out in exactly this part of the world, and I worry about the elderly members of my family as a result. That's the timetable which we had a look at. So we'll sort of discuss now and then go into the breakout room and so on. So here is the talk. Now, I don't know how many of you had a chance to look at it, and I won't bore you by going through the whole of the talk. But just to kind of give a précis, what this talk is trying to do is to explain the way that mathematics is used in climate change research, and to also say a little bit about why we believe climate change is happening, what's going to happen in the future, and some mitigation strategies that we can put in place to deal with it. So it's a chance really for people to kind of learn a bit about climate change. And it's a talk I give in various guises to quite a lot. I give it to schools, and when I give it to schools, I combine it with a workshop where the students then go off and play with various bits of computer software to actually look at what's going on in the talk. So the talk itself starts with a description of the various kind of ways that professional climate centres operate, and the kind of ideas behind the very big models that they're using and the way they gather data. Then I take some time in talking about the current evidence for climate change. So the evidence is things like the fact that the Earth's temperature has clearly increased a lot since industrial revolution. This is something we can simply measure with thermometers. And in the last 10 years, we've had the 10 hottest years ever. And the amount of carbon dioxide in the atmosphere is increasing very rapidly. And the oceans are, the sea level rise is going up, and we're getting more and more frequent rainstorms. So this is kind of evidence that I provide for climate change. Interestingly enough, if you go onto my website and actually look at this talk, you'll see that there are about 1,500 comments on it from various people. About 100 of those are complimentary, and the other 1,400 are climate deniers trying to tear me limb from limb. And it's interesting to see how they try to either ignore the evidence or tell me why I'm wrong. So that's an interesting issue in its own right. And we can maybe talk a bit about that later on. Then the second part of the talk is actually developing some simple models of climate, models which are not out of the reach of young people at school. So, for example, the simplest model of climate we have is what's called the energy balance model. And the energy balance model says that the Earth receives energy from the sun, and some of that gets through the atmosphere down to the Earth's surface. Some of it is reflected by the Earth back into space. And then the energy which gets it onto the Earth's surface then heats the Earth up. And when the Earth gets heated up, it starts radiating that energy back into space in the form of infrared radiation. And then that infrared radiation some of it goes back into space, but most of it goes back into the atmosphere, where it's absorbed by the atmosphere and probably reflected back onto the Earth's surface. This is what we call the greenhouse effect. And the greenhouse effect is dominated by what we call greenhouse gases. So that is carbon dioxide, methane, and water vapor. And the more of those you have in the atmosphere, the more energy gets reflected back. And therefore, the Earth gets hotter. And the energy balance model is a way of putting all this into a formula, so you can predict the temperature of the Earth given the amount of carbon dioxide and other greenhouse gases in the atmosphere. So that's the energy balance model. It gives you an estimate for the temperature. And it's an estimate which works. And it's an estimate which doesn't involve solving anything more than a couple of quadratic equations, which is kind of nice. And what's wonderful, and the students love this when I do them in the school, do this in the school, is we take the same formula and I say, well, look, let's, instead of putting in the parameters for the Earth, which we know, let's put in the parameters for the Moon. And they put the parameters in for the Moon, and that gives you the temperature of the Moon, and it works out to be exactly right. So you can use the same formula to predict the temperature of the Moon and the Earth, and you can do Venus as well. And it kind of blows them away a bit to think that this mathematical formula can tell them what the Moon is doing, even though we haven't gone to the Moon. So I love that. And as I say, it only involves solving two quadratic equations. So that's the energy balance model. And you can use that to predict into the future to a certain extent. And then the third part of the talk looks at predictions into the future and a kind of a scenario called a tipping point, where a tipping point, you hear a lot about this in the climate literature when people say, have we gone past a point of no return, so that it doesn't matter what we do, we're going to be in a bad state. That's called a tipping point. And we talk a bit about those. Personally, I don't think we're at a tipping point. I think we can recover, and the models that we've generated show that we can recover, provided we not only stop producing carbon dioxide at the level we are, but actually start reducing the carbon dioxide and start to try taking it out of the atmosphere as well. And that can all be done through mathematical models. And then the talk finishes on a kind of note of talking to young people about various ways in which they can personally do something about the climate. I used to give this talk without that, and then the teachers told me off for saying, all you're doing is depressing our students. Please do something a bit better. And so I felt, well, fair enough. You know, I don't want to leave people thinking they're powerless. Let's actually talk about how young people, or anyone really, can go and do something about it. One other thing is, I should say, the talk comes to do with various visual aids. So this is one of my favorite visual aids. I don't know if you've ever seen one of these. This is a chaotic pendulum. There we are. And I use this to demonstrate how things cannot often be as predictable as you'd like due to the impact of what is called chaos theory on our atmosphere. So that's a chaotic pendulum to describe chaos theory, and I thoroughly recommend that you get hold of one of these, or get hold of it on YouTube if you're interested, as a way of demonstrating predictability or not in the atmosphere. Okay, so that's what's in the talk. Let's move on now. So here's a question which I'd like us to kind of discuss now for the next 20 or so minutes, and then maybe in your breakout rooms, which is, we know climate change is insanely complicated. The computer codes that we use for the Met Office have billions of lines of code. Well, no, maybe millions of lines of code, but they're solving billions of equations. So the question we really want to ask is, how might mathematics, or the way we teach mathematics, be used to contribute to a better understanding of climate change? Okay, so this is, I think, a very relevant question to today's meeting. And I'd like to kind of hope we can have a discussion about this. And I've broken this down into 3 subheadings, which relate essentially to 3 different areas of mathematics. So the first is, I believe that one of the key things that mathematics can do is to provide evidence for policymakers or for the public or whoever that climate change is actually happening. Okay, that it isn't just normal variation in the Earth that we'd expect anyway, that something is actually happening. And this is where mathematics can be really useful, particularly statistics. Now, my impression, talking to my undergraduates in particular, is that many of them find statistics maybe one of the lesser interesting parts of mathematics when they first meet it. I hope that's not universally true, but that's simply an observation. And statistics is vital in understanding the data that we get from measurements of the climate and the change in the behavior of our weather systems, and also gives us a way of understanding the uncertainty behind this. So, you know, again, people say, oh, the climate's always been changing. How do you know what you're seeing isn't just natural variation? And that's part of the way of extracting information from data which can be uncertain. So that is one area I think is really, really important. And I'd be interested in people's views on this, whether they have seen the data about climate change, whether they have tried to understand this using statistical tools or involve that in their teaching. So as I say, statistics is very important, both in giving us evidence for climate change happening, but also arguing the skeptics. I mean, if they say, oh, well, you know, it's all not really happening, what you should always get with statistics is some estimate of the uncertainty, and I'm sure David would totally agree with me on that, and that comes in. The second thing that mathematics does, and this goes back to the point you just made, is it helps us predict the future of climate change. And this is where we try to explain what's going to happen rather than just observing what's happening. And I think there's a lot of confusion here in the kind of public view as to how this is done. But this is actually very much my kind of day job, as it were. And the way climate models work is you start with the laws of physics, laws that we understand really well, and you build mathematical models from those, which are largely based in terms of differential equations. And then you put those differential equations into a computer, and that produces answers. And those answers are what you then use to try to predict what's going to happen next. And we put a lot of effort into getting these models right. And as I explained, that there was a simple one to do with energy balance, but that is one of what we call a hierarchy of models, which become increasingly more complex. And I put uncertainty here again, and this is a problem I face all the time in my work, in that any mathematical modeler knows that a model is an approximation of reality and therefore has uncertainty associated with it. And we want to convey that uncertainty, but we want to do it in a way that we don't make everyone think that what we're talking about is rubbish, that we don't really understand what we're doing. And this is one of the big challenges I have talking to policymakers, is to say, well, look, we know climate's going to happen. We're not precisely certain about what's going to happen, but we can give you a good kind of level of our of how accurate we think our predictions are. And this is something, again, I'd be very, very keen to explore more in the context of a classroom as to how we can get across the business of how we model the climate in a way that young people can understand. So again, I'd be interested to hear experiences of this. Well, one way I do this with classrooms is I go in with a computer with various climate models in them. I talk about what's going on, and then the young people can then play around with those and see how they make predictions, determining the impact. So this is, again, the harder part of modeling. So I get data from the weather, from the Met Office, which is what they think the temperatures and winds are. I believe that. But then trying to model the impact of that on human behavior, and even harder, working out the effect of mitigating strategies is harder still. But this is something we can do. And I think the example you make is a good one. So you can assess the relative impact of, say, changing, banning all long-distance flight as opposed to changing agricultural practice. That is something you can model reasonably reliably. Well, I can't say quite what the answer is yet, because we're still trying to understand it all. But and we're going through an interesting experiment at the moment called COVID, where we can start to monitor we're actually getting data now as to what the impact of not flying so much is. And that is actually rather relevant and useful. But this is being used to inform. I mean, there are two things. We want to understand what the impact of climate change is and what we can do to build resilience and move forward. And of course, that's insanely relevant to young people, because it's their lives that are going to be more affected. I thoroughly agree with you. This is stuff we can do, and we should be doing it. And you can build into these climate models relatively easily. You can say, well, let's suppose that we cut all our carbon dioxide emissions into the atmosphere. How's that going to change the temperature? Well, you can do that. You can say, if I cut the amount of, if I plant so many forests, what's going to happen? Again, you can do that. And I think our students are highly motivated to get on and doing all that. And I just put my final slide up, Keiko, because I think it's very related to exactly the point you made. So if I'm talking about this to either policymakers or to school students, I want to say, how do we build our models? What are the assumptions that we put in? How do we test them? Can we trust them? And is it reasonable to make decisions based on them? And that applies not just to models for climate, but Beth will understand this one very well. How about algorithms for producing A-level results? Are they tested? Can they be trusted? And should we make decisions on them? It's not a dissimilar question that we have there. So that's kind of what I want to say at this stage. Are there any other comments? So Helenka, these are marvelous questions, by the way, Helenka, thank you very much. Helenka says, uncertainties in the realm of risk factors. If we have been slowly getting hotter since the medieval era, then the risk factor uncertainty may be declining, and maybe it's more likely to get hotter in the future. Yeah, that's very reasonable. As we get more information, so our level of uncertainty declines. And this is, there's a fancy word for this in meteorology. We call it data assimilation. So you have a model which has a ton of uncertainty. And as you make predictions day after day and bring in more and more data, so that gets assimilated into your model and reduces the uncertainty and improves the model. And this is a kind of combination of statistics and modeling. It's one of my favorite areas of work, actually, data assimilation. And a lot of it's done that. And the example I use is, you look at your thermometer on the wall, that's your meteorological data, and it says it's 30 degrees centigrade. But everyone in the room is wearing coats and shivering, and there's icicles growing on the windowsill. And from that, you might assume that the data you're getting from the thermometer might not be particularly reliable. and it's cold out there. So that's how you then compare data with knowledge. So I'll finish there.